This is a typical frequency response function magnitude. It's actually called a sensitivity function because it says how sensitive is this thing to acceleration coming in. And you want a 1-to-1 ratio between the acceleration you're measuring and the voltage you're measuring. That way you can say this many volts is this many G's, right? So the bandwidth of this thing goes, and they don't have the numbers here, but it goes down. This is your working range. You go down 3 dB here. It's got a huge resonance. Many of them, they're not quite this big, but it does have a resonance. So the upper 3 dB range is limited by the resonance of the accelerometer. And if you don't take this into account, I mentioned to you, because I have 2 classes, sometimes I tell different stories in different classes. I told you about the sugar mill control, didn't I? That must have been this 3 p.m.? Okay, a good friend of mine who works at UCSD used to be in Australia at the National University, and he's an adaptive controls person. And the idea behind adaptive controls is you don't know the transfer function of the plant. So what happens is you do measurements, like what we do in 573. You do measurements, and you estimate. You estimate the poles of the plant. And then you, based on those estimates, you modify, you adapt your controller to handle those plant poles, right? Because if the poles can be changing, systems can be time varying, right? If you think about just your car, when the oil is cold, you have high damping. When the oil is very warm, you have very low damping. So the resonant structure is changing with time. So what these adaptive controllers do is they identify the plant transfer function, and then they modify the controller form so it adapts to that pole, right? If the pole goes somewhere else, remember in pole placement, if the pole's here and you want to get it on the root locus, you have one angle. But if the pole is moved over here, you need another angle. So you adapt the controller. So the idea of what that applies to, well, here is they were in Queensland, near Brisbane, and they were up in a sugar mill, which makes sugar. Okay? And Queensland is noted for its beer. And Bob was with this French researcher, Yves is his name. And they were up there, and it was summer, which is our winter. They were up there around midnight, could not get the controller to stabilize the system. Just was not working. And so finally, this is from Bitby, he told me directly, he said, yeah, about midnight or 1 in the morning, Yves says, this is crazy. We're not getting anywhere. It's dripping, sweating, wet, hot up here. I'm going to go down and have some beers. Because you guys don't get the good beer from Australia, I'm sorry. You think Foster's is good? That's why they ship it here. I didn't say that. Anyway, what Bitney did is he got frustrated, and so he took out an oscilloscope. You know what those things are? Anybody ever used one of those? And he measured what was going into the controller. And lo and behold, it was a 50 hertz ground loop. You know what a ground loop is? It's when you've got a floating ground or a ground that's not solid. And so if you're running on AC, like in our country it's 60 hertz, in Australia it's 50 hertz, you'll get this 50 hertz hum. It's noise. It has nothing to do with the controller. It's electrical noise. And what was happening is the controller was seeing that oscillation and taking it to be a plant pole, a low damped plant pole. And so it had a pole at 50 hertz that it was trying to accommodate. Except there was no pole at 50 hertz. It was a ground loop. And so this is one thing you have to be careful about with accelerometers. If you're doing adaptive control and you measure with an accelerometer, and this accelerometer amplifies a small acceleration out here, your controller is going to think that this peak is a resonant peak in the plant. And it's going to go after it to try to tone it down. But there is no resonant peak in the plant. It's simply your accelerometer that had a high amplification at that frequency. So you've got to be really careful when you're doing especially adaptive control. But even if you're doing regular control on this, a lot of plant identification uses electronics. And if in your FFT analyzer, your electronics tell you, oh, we've got a resonance at 22,000 hertz or whatever it is, then you're going to design your controllers for that resonance in the system when it has nothing to do with the system. So I'm not a controls person. I work on the periphery of control. I try to make controls work better for people. Because there are too many controls people that's very mathematical stuff and it's beautiful stuff, but they don't know the periphery. They just know the control. So that's another example of FRFs having to do with accelerometers. Then there's one with rate gyros, which is very commonplace in your business. Our business, I didn't say that. We're all Aeroes at heart. And so this is a whole hodgepodge of FRFs for various rate gyros. So you can go on and look at that thing and see what is the frequency response function. In fact, most rate gyros have programmable FRFs. You can set them to 200 hertz, 500 hertz, depending on, for navigational purposes, you want very low frequency bandwidth because you're measuring it very slowly, right? But if you're measuring robotics, which is very fast motion, you want high bandwidth rate gyros. So that's an example there, and then I happen to actually stumble upon this thing, which caused me to kind of line that.
Okay. How about U of T? Eigenfunction?
MIT.
Same thing, right? I would think of the input is U of T, the output is lambda U of T, the derivative of the output. If the output is lambda U of T, what's the derivative? Lambda delta. So unless we're trying to make a lambda, unless we're trying to make a U function out of the sum of the delta and the U.
Some understanding of frequency response function.
So the answer is that the first three are eigenfunctions and the last two are not.
So if perchance
so now,
you have a
what's
severe
have
case
to,
of
insomnia, I'm thinking about
or you have some kind of YIM to study at MIT, go for it. All right, let's get into the material at hand then. All right, let's get into this stuff now. This is the example stuff that we were doing last time, and this is where we ended up. The book has this as a homework problem to derive the mathematical formula for the frequency. This is a picture for a lead compensator. Right there. So the compensator phase has a maximum, doesn't it? And that was what I said last class is we want to use that phase in lead compensation. In lag compensation, we don't want to use the phase. We want to use the amplification property of the compensator. But for lead compensation, since it adds phase, why does adding phase to the open loop help? That's a semi-rhetorical question because this gets to be really seat of the pants. You have to say, why did you specify a 60-degree phase margin? Well, because that seems to do a good job. That's one reason. It's very kind of fuzzy in terms of, like with poles, we know exactly what we're doing when we specify a damping ratio or a settling time or things like this. But when you're specifying a closed loop phase margin, things get a little murkier, except in the case of time delays. Remember, time delays, a time delay to this system does not affect the magnitude. A time delay is this. T of S, transfer function of the time delay is e to the minus s delta, where delta is the amount of the delay. So when you put s equals I omega, you get e to the minus I, or I times minus omega delta. This is your theta of omega, isn't it? And it's linear in omega. Theta of omega here is just minus delta times omega, right? So when you multiply this thing by that plan, since the magnitude of this thing is 1 right here, isn't it? E to the I theta, remember that's cos theta plus I sine theta, magnitude 1. It doesn't affect the magnitude at all. All it does is subtract phase. So if you've got a phase margin of 30, remember, a phase margin of 30 degrees means at the gain crossover frequency where the magnitude of the open loop is 0 dB or 1, our root locus, right? That's one of the 2 root locus conditions for the open loop magnitude to be 1. Your phase, suppose your phase is 30 degrees above negative 180. Because if it were negative 180, you have a pole, a closed loop pole at that omega. Because that's the root locus angle criterion, right? Again, this ties intimately with the root locus, the idea of a phase margin and a gain margin. So if you have a 30-degree phase margin, but in fact you have a time delay, all right, then you got a problem. Let's go to this. Suppose this were a system. Well, actually, the gain. We'll get into it. So that's the other reason for you want positive phase in the open loop, because any time delays are going to drop the phase. They're going to make the phase more negative, and as omega gets bigger, they make it really negative. Right? This thing is linear in delta in omega. For very tiny omegas, you get no phase delay. But as omega gets bigger and bigger, this phase curve would start doing, suppose it started having an effect right here. Then instead of this phase, you'd get this one. It'd be dropped a little bit. Then you keep going higher omega, and the drop keeps getting bigger and bigger and bigger, and before you know it, you can destabilize the system with time delay. So that's a big reason for looking at phase margins. So in the last class, we ended up with this. Deriving the mathematical formula needed to understand this compensator. Okay? And now, there is a disclaimer here. Where is it? Yes, there it is. If you don't like math, take a breather. Go to Greenland. Just put your head down and sleep. This is not going to be on the exam. I'm doing this for people who like to see how the math is used to get the formulas that you're using, rather than just grabbing plug-and-plug formulas. So sometimes I think that's helpful to exercise of different parts of your brain. So, all right. This is what we ended up last time. We have a transfer function for this compensator that looks like this. Remember, I told you why I like writing it like this. The authors don't write it like that. They write it as Ts plus 1 over alpha Ts plus 1. I don't like it. I like writing it as omega 1 plus I omega 2, because these are the break frequencies of the compensator. And you're designing in the frequency domain, so it's good to work with frequencies when you're working in that domain. What's the static gain of this compensator? Or the low frequency gain? Think omega low. Or put your microphone closer to your mouth. Come on! Think of omega really low. What's the gain of the compensator? 1. It's omega 2 over omega 1 times omega 1 over omega 2, which is 1. That's why this is out here, to give this thing unity static gain. Okay. All right, so the magnitude, we know how to get the magnitude. This is just the magnitude. We keep that, but the magnitude of a complex number is the square root of the real part squared plus the imaginary part squared. There's our magnitude. We also know that the angle of this thing is the arctan of omega over omega 1. Because when you have a complex number, right? A plus IB, the angle of it is the arctan of B over A. That's just basic treatment. So here's theta. Okay, and now what we want to do is we want to find the frequency at which this theta of omega is a maximum. Because we need this. We need this to design a compensator. What we're going to do is we're going to say, I want to put my compensator at this frequency. So I need to know how this frequency omega max, that we're going to maximize this thing over, how it relates to, there's two parameters in this compensator, right? Omega 1, omega 2. I need two equations. One of them is going to be the expression for omega where this phase maximizes. Because then I can say, I want the compensator at that omega. That gives me one equation, and then I'll just need one more equation, which is how much angle do I want at that frequency. So we need two equations and two unknowns. All right, okay, here's the first of the two tricks that I use to solve this thing. So I say, out of the Brit, recall the trig identity. Tan of theta 1 minus theta 2 is tangent of theta 1 minus tangent of theta 2 over the quantity 1 plus tangent of theta 1 times tangent of theta 2. I'm sure you all covered that in sufficient detail in your calculus course. Yes. Or even perhaps in pre-calculus. Sure, boy. So, I had to hunt for that thing. Because I wanted to get rid of those arctans. Right? Theta is an arctan. Remember, theta 1 is the arctan of omega over omega 1. Theta 2 is the arctan. So if I can do a tan of arctans, I get the tan of an arctan, which is just omega over omega 1. So I started searching the trig identities for tangents of theta functions, and that's what I got. All right, so then when you shove those two in, theta 1, theta 2, you end up getting this. So here's phi of omega. It's the arctan of this whole works. Then there's one more little trick, which is an invaluable trick. And that goes with this. If I have, well, let's just look at it in that particular example. I want to maximize this. How do I get the maximum? Take the derivative and set it equal to 0. What's the derivative of the arctan function? Yeah, 1 over 1 plus x squared, whatever it's the tan of, right? But then you have to use the chain rule. You have to go inside because you have f of g of omega, don't you? So you first take the f of g, then you take the g of omega, and I'm telling you right now, you can ignore the tangent. Just ignore it. Why? Let's look at the arctan function. And again, we're only going from 0 to 90 degrees. This is the tan function, arctan function. Where is its slope 0? It is never 0. So by taking this thing and setting it equal to 0, since this thing can never be 0, I don't have to worry about it. I can just go directly inside and take the derivative and set it equal to 0. Makes life a whole lot easier when you're solving for the omega where it's missed. So that's the second little trick that I used. And then it's talked about right there in the chain rule. And there's what you get. The rest is algebra. It's polynomials, but it's not bad. It's quadratic. So omega maximum, the frequency where that maximum phase occurs, is at the square root of omega 1, omega 2. So let's write that down. The frequency omega at which theta of omega is max, which we call omega max, is omega max is the square root of omega 1, omega 2. Okay? Now, before we go on to the next equation, let's think about what happens when we do log frequency plotting. Because remember, our frequencies are in log frequency, aren't they? Right? We're using semi-log x. So the frequencies are spaced logarithmically, and the amplitudes are in decibels, so they're just linear in decibels. So what happens when I log this?
1/2 log omega 1 plus log omega 2.
Do you have a life? It's the average. It's the average. So on log paper, that peak sits directly between, right in the middle of the log of omega 1 and the log of omega 2, which is why that thing looks symmetric in semi-log paper, because it's sitting right in the middle. By the way, in reference to that question, I was working for the Air Force back in the early 2000s, and I was in D.C., and we had a conference on Friday, and I said, well, you know, you guys, I'm going to be around for the weekend, and, you know, if, like me, you don't have a life, we could get together and meet on Saturday. And my funding officer kind of shook his head, and they said, no, we've got plans. And then he took me aside and he said, Peter, I know you're unusual, but don't tell these people they don't have a life. Most of them really don't have a life, and they really don't like to hear this stuff. That was bad. I burned a few bridges on that weekend. All right, so that's one. So now what we have to do is we have to find what is the phase at omega max, because that's where the phase is maximum, right? So you put that omega max back in the formula, and now remember, when it says it can be shown, you're in for a trip. When it says it's easy to show, plan on just a couple pages. So it's easy to show that you get this. This is the magnitude at omega max. Okay, before we get to the phase at omega max, get to the magnitude. So this is the magnitude m at omega max is equal to the square root of omega 2 over omega 1. Now, what's the high frequency gain of the compensator? Let's go back to the compensator form and say, what happens when, does anybody remember when omega is huge? Remember, it was omega 2 over omega. I'll just go back and show you. It's Friday. There. What happens when omega or s, it doesn't matter, when s is monstrously big? You ignore this, and you get s over s. And so your high frequency gain is omega 2 over omega 1. So the high frequency gain, omega m of, as omega goes to infinity, is equal to omega 2 over omega 1. Now again, let's go to decibels. We're going to take 20 log of this, right? So in dB, this is 20 log omega 2 over omega 1. What's this in dB? Who said that? Who said it? You're all going to be punished one by one unless you tell me who said it. I was one of 9 kids. By the time it got to me, no one had confessed yet. Because we always start from the top down. All right. right? So in graphically, it's halfway to the total maximum gain. So there's some really nice, simple symmetry in this thing. If you go to this plot here, get rid of this. Because of the scales chosen, because of the log frequency scale, and because we're using decibels, you see a really nice symmetry here. The peak phase is at the geometric mean of omega 1 and omega 2. It's very symmetric. And you're halfway in decibels, you're halfway to the total high frequency gain of the compensator at that maximum frequency. So it's really nice in visual sense. Now the last thing we need to do is we need to actually get there. Now we derive the expression for theta of omega max. And this is where my geometry, because I really like pictures a lot, I just use pictures. And from the pictures you find out that alpha, and I define alpha as omega 2 over omega 1. So again, let me get rid of this thing. This is one important property. I'll write it in a summary form here. This is one of our equations. Omega max is the square root of omega 1, omega 2. M of omega max in dB, well, it doesn't even need to be dB. We can just leave it as we had it. And the third equation is theta of omega max is 1 plus sine alpha over 1 minus sine alpha, where alpha is omega 2 over omega 1. You can just get rid of the alpha if you want. Sometimes I get lazy in my word equation editor. And it's much easier for me to click alpha than it is to click omega sub 1 divided by omega sub 2. So that's the third equation. It's just from that picture. Okay. All right. So that's it. Now let's go to the book for a minute. Oh, we got 10 minutes. I was going to say, we're done. All right, so then he goes through all of this stuff. Ooh. Oh. Not pretty. Why is that so ugly? Huh. Any ideas? All right, anyway, this is what we ended up with, except notice, and my apology is really not very sincere, but I apologize for using different notation than the author. You're going to have to just kind of reconcile the two different notations. But we get the same pictures, right? This is the magnitude. This is the phase, and he shows it right in the middle there with this. I'm sorry, I just really hate TD. I have no idea what TD is. I'm in the frequency domain. Ugh. Then he says, let's go to an example. All right, so as an example of designing a lead compensator, let's repeat the design compensation example for a DC motor with this transfer function. It also represents, by the way, a model of a satellite tracking antenna. This time, we wish to obtain steady state error, blah, 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 so we get a steady state error. So he's going to get a steady state error, so he lets k equal 10. So now the transfer function is 10 over that. Okay? Right? Just put a 10 in it. And then what happens is you get this Bode plot for the open loop. So there's the Bode plot for the open loop. And if you look at this thing, we want to get a phase margin and we want to get a gain margin. Okay? So what he says is, okay, for currently without any lead compensation, we go to the 0 dB point, which these guys, they try to be so engineering and then they put magnitude instead of decibel. What a hoot. So you go to where the magnitude is 1. Right? Because they're using log y-axis. We use b. So you go where the magnitude is 1, and you find out how close is the phase to negative 180. Was 20 degrees above negative 180? Okay? All right? And so what you say is, let's see, I want a phase lead of 40 degrees. Okay? To be safe, all right, here's what it says. Let's see. Crossover frequency is at 3. Additional, the phase margin is only 20 degrees if no phase lead compensator is added. Blah, 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 blah. So he wants to add a phase compensator to bump the phase up to 40 degrees. All right? Now here's the deal here. If you use the maximum phase of the compensator, you're at 20 degrees right here. No, it's at 1. Oh, no, I keep looking. Yeah, this is it, right? You're at 20 degrees, and you want it 40 degrees. So how much must your compensator add? Come on, Smarty. Just give me your time. 20 degrees. So that's one of your design equations. You set this equal to 20 degrees, and now you've got one. And of course, you have to convert this. You've got to be real careful to degrees to radian, right? This is 20 degrees, and you want to put it in the radian form. So that's one of your two equations. What's the other equation? Where do I want to add that 20 degrees? Well, where I only have 20 degrees, that's how I got that 20 degrees, as I said, right here where the gain crossover is 1, or 0 dB, I have only 20 degrees above 180, and I wanted 40. So I said, we need another 20 here, at that frequency. That's omega max. So I don't know what it was, around a little over 2, maybe 3 radians per second. See, then you just solve this. So what's going to happen when you solve this? What's going to happen is you are going to raise the phase up to 40 degrees. Guaranteed, it's the math. What else happens? Does this compensator affect the magnitude at that frequency? Yes, because at phi max, at omega max, it raises it by alpha dB over 2. Or by the square root. See, this is why I don't like this guy. Everybody uses dBs. All right? Or by the square root of omega 2 over omega 1. So here's the problem. The problem is that you say, yeah, here's where I want it because I'm only above by 20 degrees now where it's crossing over 0 dB, and I want it to be 40 where it crosses over 0 dB. But then when you do that, this point that was 1 now gets raised up. And so your unit magnitude crossover has been shifted to the right to here. You see what it just happened? When you put the compensator at omega max, it does give you the maximum phase at that frequency. But it also changes that point, that magnitude point. So then what happens in reality is this increase, because the compensator has amplification too, right? It starts at 0 dB and then it goes up. So it's amplified, and so this whole thing has been raised up, and now this is the crossover. But this one was only 5 degrees or whatever, I don't know, 10 degrees. So you lost some of your phase. So that's why the authors say, beautifully, I love this. Let's see, there it is. With some trial and error, that's what we ended up with. So this is not a clean process where you just get 2 equations, you solve it, and you're done. Okay? Now what you could have done is you could have done something a little more clever than this with this picture here. And you could have said, all right, I know roughly how much phase I want. I want 20 degrees of phase, right? Remember, because we had the 20? But I'm going to put 30 degrees of phase. I'm going to compute 30 degrees of phase. Okay? And I'm going to do it. This is alpha. All right? So if I put 30 degrees here, I know what alpha is. I know what the ratio is. Right? I'm not saying where I've put it yet. All I'm saying is I know what the ratio of omega 2 to omega 1 is. Because I'm adding 30 degrees of phase, even though I only thought I needed 20. Then I compute this. Right? You can now compute this thing. And then you go over to the magnitude plot where you're currently down that many dB. Because you know if you put it there, it's going to raise it up to 0. And it'll be the 0 crossover point, or the unity crossover point. So it's a little more logical iteration than just kind of shooting from the hip. But this is what we're going to be covering for the next probably week and a half. And a little bit of this will be on the exam. But we'll also cover this in functionality after this. Have a good weekend.
We're just last time.